Okay, today we are talking about 6.6. This is part 1 of 6.6, and we are going to um be talking about polar form of complex numbers. Okay? And that's going to lead to the second part of 6.6, which is de Moivre's theorem and the nth roots of unity. So, just to review quickly, what is a complex number? Complex number is something with a real and an imaginary part. And at some point in the past, we have graphed them, with this being the real axis and the imaginary. That's the point there. This is also sometimes thought of in terms of vectors as 2, 3, or to talk briefly about vectors being I hat and J hat, with I hat axis, J hat axis. Um, so we can plot various vectors. So we can give a vector, call this U. I can call it my U vector, I can call 1 plus 3i. That's the, or not 1 plus 3i, 2 plus 3i. Yeah. I can give my v vector as 2 minus I. So again, here in more normal vector form. And when I add u plus v, I get 4 plus 2i. Or when I add the vectors, I get 4, comma, 2. And it works out to be the same either way. Okay? So let's take our 2 plus 3i and let's convert it to polar form. I'm going to show you how to do that. So here, I'm going to make this a little bit bigger. So polar has a radius and an angle. Let's just make that theta better. So the polar form of any complex number, we're going to use z a lot for complex numbers, is r cosine theta plus I sine theta. I'm going to show you why that's true. R is known as the modulus. Remember, we've talked about this being with a vector, that being the magnitude. With a complex number, that's R. If we're in A plus BI form, we're just going to use the Pythagorean theorem. And I'm going to put the square root in right away. But R squared equals A squared plus B squared. Theta, we can find with an inverse tangent often. So this is called you need to know this term, modulus. And that's essentially the radius. The argument is the name for the angle. Now getting heated in this argument. But that would be the inverse tangent of B over A, sort of. Because it could be over in a quadrant where inverse tangent doesn't go. You need to interpret it correctly. But this is used. I suppose I probably shouldn't say that that's always what it is, because sometimes we need to figure that out from the graph, and we're usually going to use inverse tangent. But let's talk about this one. So let's first get the argument, or the modulus. R is equal to square root of 2 squared plus 3 squared. That's square root of 13. Y, x. So we know here y is 3. X here is 2. We know, though, if we don't know y, we know that y is multiplied by, maybe I shouldn't say y, I should say b and a. We know that the sine of theta equals b over r, or r equals b, no, r sine theta equals b. And likewise, a is going to equal r cosine theta. Again, that's cosine theta equals a over r. So my complex number is a plus bi. I can substitute. A is r cosine theta. B is r sine theta. And then there's an I attached to the end of that one. Actually, maybe I'll put the parentheses in a slightly different spot. I'm going to put the parentheses around the sine theta, because this is one term, r sine theta I. R is in common, so I should probably cross my z's. So we can factor it out, and there is my basic polar form of a complex number. And we get those simply by whatever r times sine theta is going to give me the b. So let's put my 2, 3. Let's finish putting my 2, 3 in there. So we got their modulus square root of 13. To get my angle here, I'm going to use inverse tangent. This is in a quadrant where inverse tangent is going to work for me. And I just have to calculate that here for a second. I get 56.3 degrees. So my complex number is square root of 13 cosine 56.3 plus I sine 56.3. I could have also done this in radians, but there's my complex number in polar form. Now you might go, why is polar form useful? We'll see a little bit in the next lesson. But it really extends beyond what we do in this course. A lot of the things we're doing, and I've told you this with E, they become more apparent why they're nice later. But the job in this course is to get you introduced to them, get you comfortable with them. So you're just going to learn how to use it. And then the applications come really later. They're a little more advanced than you want to do in this course. Okay, so we're going to do a couple examples of converting. This is example 2. We've got 1 minus square root of 3 I. So if I graph that, and that's always important here, somewhere over here, 1 negative square root of 3. To get my modulus, I do square root of 1 squared plus square root of -3 squared. That's square root of 4 or 2. To get my angle, this one I should be able to just use an inverse tangent on as well. Negative square. If as long as I take the negative with it, I should get the right angle. And that will give me, in radians, 5 pi over 3. Okay. Again, I could read this off the unit circle. Negative square root of 3. The sign is negative square root of 3 over 2 because it's opposite over hypotenuse. So I get the 5 pi over 3. If you do it on the calculator, you'll get a decimal equivalent to negative pi over 3, which when you add 2 pi gives you 5 pi over 3. If you're checking answers in the back and you want to know if you're the same, try doing that. Make sure you're in radian or degree. Be specific. This one specifically asks me for theta between 0 and 2 pi. Shouldn't really have the equals on the 2 pi because that's the same as 0. So that tells me it has to be radians, and I can't do the negative. But if you had that, it's the same placement. You just missed this part right here, and you have to follow that. So we have a radius of 2. My complex number, here we'll write it out. Two cosine 5 pi over 3 plus I sine 5 pi over 3. And there, I've done my conversion. I'll do another color for part B. Part B here is -3, -4. Wait, no comma. -3 minus 4i. Again, I'm going to graph this. -3, -4. It's right there. Make my triangle. This is my angle. If you do the inverse tangent, that. Okay, radius equals the square root of, I'm not going to show my negatives because I know a negative squared equals positive. That's 9 plus 16 is 25. Square root of 25 is 5. This is a 3, 4, 5 right triangle. My angle, oops. Four over 3. It's -4 over -3, but that gives me 0.927. My 0.927 is that angle right there. So to get the actual angle, I must add pi. And that is equal to 4.07. So -3 minus 4i is equal to 5, my radius, cosine 4.07. And this is again in radians, plus I sine 4.07. 4.07 radians, yes. And there we go. That is my answer. So that's converting. It's not bad if you draw the triangle and you take the work and you think about your angles. Okay. I'm going to talk about a couple of equations for multiplying in polar form and dividing in polar form. So I'm going to talk about multiplying. And these are in your packet or your Bible. There's a page that talks about has vectors and polar form of complex numbers on it. And if you want to see the proof, it's on page 553 in the book. And it just uses distribution and um, the sum and difference identities that we talked about in chapter 5. So all I have to do here is multiply the moduluses or the radiuses and add the angles. And then the second parentheses closes the one around the cosine of an angle plus I sine of an angle. So that's my multiplication formula. My division formula is similar, except I divide my radiuses or my moduluses, and I subtract my angles. This, like all division, does imply that my denominator is not equal to 0. It's not the complex number 0 plus 0i. So and we'll take a look at example 3. And we're going to multiply some complex numbers. C2 is my second complex number. So Z1, Z2. When I multiply these two numbers together, I get 25 root 2 times 14. Remember, I'm going to add my angles. Negative pi over 4 plus pi over 3 plus I sine negative pi over 4 plus pi over 3. I'm going to show the fraction addition on the side here. So I'm going to make that pi over 4 is 3 pi over 12. Common denominator is 12. Pi over 3 is 4 pi over 12, so that is pi over 12. My numbers in front, 25 times 14 is 350. We're going to convert this back to regular form or rectangular form. Now, I could have converted each one of these into rectangular form and just multiplied them. Or I can do it this way. If you want it back in polar form, it's easier to do it this way. But if not, to get my A, I do 350 square root of 2 times cosine of pi over 12, and I get 478.11. 350 square root 2 sine pi over 12. We'll do all of that, and that's times I. I stick that into a calculator, I get 350 square root 2 times sine pi over 12. I get 128.11 I. That's my rectangular form. My polar form is right above it. They are both equivalent. Let's do example 4 versus division. Here we've got complex number 1, 2 square root of 2 cosine of 135 degrees plus I sine 135. Complex number 2, 6 cosine 300 degrees, I sine 300 degrees. So I plug it into my formula. 135 minus 300. Oops. This one is probably easier because if you converted them both by hand, you'd then have to rationalize the denominator to do your division if you converted first. This is probably actually easier to do it in polar form first. Square root of 2 over, I can reduce the 2/3, cosine negative 165 plus I sine negative 165. To convert to rectangular, I'm doing square root of 2 over 3 cosine negative 165 plus square root of 2 over 3 sine negative 165 I, giving me negative 0.46 plus negative 0.12 I in rectangular form. Okay, that is it for polar form of complex numbers. We'll talk more about the rest of the section in another video.